Okay, this question is not anything new, but it's tricky because you have to interpret everything that is going on in this problem. An arrow is shot up and reaches a maximum height of 30 meters. So here's the arrow number 1. It's going to go up to a height of 30 meters and then presumably fall down. It's not really that important. When the arrow is halfway up, right here, a second arrow is shot with a velocity that makes the two arrows meet at the top of their motion, at the top of the first arrow's motion. What that means then is the second arrow must be going faster. So at the same time that this one does this one is going to go this whole distance, 15. Makes the two arrows meet at the top of the first arrow's motion. Determine the maximum height of the second arrow. So one more time. An arrow is shot upwards and reaches a maximum height of 30 meters. So there's your arrow up to 30 meters and back down. When the arrow is halfway up, 15 meters, a second arrow is shot with a velocity that makes the two arrows meet at the top of the first arrow's motion. So this arrow is shot such that the two arrows get to this point at the same time. And what we want to know is we want to know how high does that second arrow go. So the key thing that relates these two is that in the time that this one goes from 15 to 30, this one goes from 0 to 30. If we take this time and then we take this motion, we should be able to find out what V1 is for this motion. And once we have V1 for this motion, we can find the maximum height. So let's consider arrow 1 first. What we're saying is when it goes from height 1 of 15 meters to height 2 of 30 meters, or if you will, a vertical displacement of 15 meters, that the other arrow goes from a height 1 of 0 meters to a height 2 of 30 meters, or through a vertical displacement of 30 meters. So whatever the time is here, that becomes the time here. Now we know for both of these situations that they're in free fall. They're accelerating due to gravity. And we don't know much else except that for arrow 1, if we're dealing with this part of the motion, then at the maximum height we know the final velocity is 0. It has to be 0 so that it can stop and turn around and come back down. So now we have 1, 2, 3, we can find the fourth. The equation here is that delta D equals V1T. Actually, sorry, this is the weird equation that we almost never use. V2T minus 1/2 AT squared. Delta D is 15 meters. V2 is 0, so that whole term goes to 0. Minus 1/2 times the negative 9.8 meters per second squared, T squared. So 15 equals two negatives make a positive, positive 4.9 meters per second squared, T squared. Dividing both sides by 4.9. T equals, don't forget square root here, 15 divided by 4.9 square root, so it works out to about 3, and then the square root of that's about 1.75. So that is the time that it takes for this arrow to go from here to 30. So if it takes 1.75 seconds, what the question says is that's the same amount of time it takes it for the other arrow to go the full 30 meters. So our question then is, what initial velocity would have been required to make that second arrow be able to do that full 30 in just the 1.75 seconds? Here we're going to use the more standard projectile equation. But I guess it's a little bit different because we're solving for a variable that we're almost never solving for. I put time in meters, time in seconds. So just doing the math for that last term, 4.9 times 1.75 squared works out to 15. Sorry, that should be in a plus 1/2 AT squared, which would have made that a minus 4.9 meters per second squared times 1.75 squared, and that a minus 15 meters. So then when that comes over to the other side of the equation, 30 plus 15 is 45 meters. So if I divide both sides by 1.75 seconds, V1 equals 25.7 meters per second. So that is the initial velocity of the second arrow. Again, just to repeat, we went from halfway up to all the way up because that's the amount of time that it said that this one took to go from 0 to 30. We found that time going from halfway up to all the way up, 15. V2 at the max was 0, so we used that to find the time. Using the time, we know we went from 0 to 30, so the displacement was 30. Acceleration is negative 9.8. Time is 1.75. Math to get to a V1 of 25.7 meters per second. Now, if I want to know the maximum height of arrow 2, I can use some of my information about arrow 2, but I need to be careful a little bit. I still know my acceleration, assuming that we're dealing with acceleration due to gravity of negative 9.8 meters per second squared. And I know my initial velocity from everything that I've just done to be 25.7 meters per second. And I might be tempted to use that time that I calculated for 1.75, but that's not the total rise time of the arrow. When this arrow hit that point, that's 1.75 seconds. How high it goes after that is not included. So I can't use that. What I'm going to use instead is the fact that if this arrow is going to stop and come back down at the maximum height, the final velocity must be 0. So there I go, I got A, V1, V2, and I'm looking for my max height or my vertical displacement. I guess I can write that to a delta D to be consistent. 2 times negative 9.8 meters per second squared. Delta D is equal to my V2 squared, which is 0, squared if you want, minus 25.7 meters per second squared. So this is negative 19.6. And delta D, meters per second squared. 25.7 squared, 660.5, negative 660.5 meters squared per second squared. Divide both sides by that negative 19.6. And my displacement is 33.7 meters. That seems remarkably close to the original displacement of the second arrow. Makes me concerned that I made a mistake. I will look it over, but in the end, the point is that the arrow goes just a little bit higher, even though it seems to have been shot with a significantly higher initial speed. So there you go, 33.7 meters.